So last time we were talking about vector valued function, and we started talking about derivatives and integrals of things. So let's jump into, we haven't really talked about integrals yet, but let's jump into just an example of a vector valued function, and just to get us used to dealing with this. Let's give it a function. What would be a good function? T squared. Another function? What? 3 minus t? Something with a sign or ln or something? Or an exponential? So e to the t usually explodes. It goes up really fast. But let's see if we can deal with that. What? Oh, well, it's okay. We'll work with this. So this is our vector valued function, and I don't know exactly how it's going to look like. We can pretend that we know how it looks like and randomly graph something. I don't know. Oh, it's 0. I'm looking at maybe when t is equal to 0. I'm just going to draw something in space like this. It looks like when t is equal to 0, the x is equal to 0, the y is equal to 3. And then the z is equal to 1. All right. So we took the derivative once. So we took the derivative once. We got r prime of t, and then we get 2t, -1, and e to the t. So this is the velocity function. We have the position. We can think about the position function as the first one. The velocity function is the second one. And then we can take the derivative again. 2, 0, e to the t. And then we have what we might call acceleration. So we can call this v of t and a of t. Plus the b and, oops. No, can't undo. Is there an undo? Undo, undo, undo. Next to the x? Oh, cool. I want that arrow so I can highlight and change this to green. All right. So these are general functions. If we want to focus on a particular point and find out information about the graph at a particular point, then we can put in that particular point. So let's say we're curious to see what happens at t is equal to 0. So if we put 0 into the position function, we would get 0, 3, 1. And what that gives us, if you remember last time, is that this thing gives us a vector from the origin to that point, and that's your position. If we figure out r prime of 0, we will put 0 in here, and then that's 2 times 0 and a -1, and then e to the 0 power is 1. And so we got a vector that looks like it's just parallel to the yz plane. Not parallel. Parallel? Yeah, parallel to the yz plane. There's no x. It doesn't move into x. And it goes -1 in the y and +1 in the z. So -1 in the y, +1 in the z. But this vector, I drew my graph wrong. Should be something like that. Which means I drew my graph wrong, because this thing, if you move this vector right at that point, it's supposed to be tangent. So let me redraw my graph. Or I could just draw a graph that's tangent to this thing. And then if we find the second derivative, and then put that 0 value into the second derivative, then we would get a third vector that would give us our acceleration at that particular point. So 2, 0, 1. So I'm going to say maybe it looks like that, and so that your acceleration vector would make a little bit more sense if it was actually on the point that we're looking at. So let's label these things. This is your acceleration vector, r double prime of 0. This is your velocity vector, v, or r prime of 0. And your position vector is the only one that starts from the origin in standard position. And if you put them all in a coordinate system like this, you get a feel for how the graph might look like. Yeah, Fred? Yes. The magnitude of the tangent vector. Yeah. Yeah. Yeah, so magnitude of the tangent vector turns out the magnitude of the tangent vector is, well, if you take the magnitude of a vector, what do you get? A scalar, right? And a positive scalar at that. So this is, if you refer back to Calc 1 or Calc 2, when you guys were doing the projectile problems, you said the velocity vector as the velocity, which was synonymous to speed back then. You just say it's speed. Actually, velocity can be positive and negative, but when you refer to speed, you refer to it as a positive number. And it just turned out that if it's positive, if the velocity is positive, then it's going in the correct direction. If it's negative, it's going in the opposite direction. And so that's the significance of the sign. But now, when we're dealing with something in 2 dimensions or 3 dimensions, the velocity can be seen as a vector. It gives not only the speed, but the direction. So it gives a direction in which it's going, and also gives the speed, how fast it's going at a particular point. Okay. So this is an important thing to remember. In this particular problem, the speed, specifically at this one point, because that's what we calculated, the speed at time 0, is going to be the magnitude, which is square root of 2. Okay. So this is a big preview of what we're going to do early next week. We're going to really dive into this whole idea of motion, projectile motion. And you should be familiar with the derivatives and their relationships with acceleration and velocity. And also be able to take the antiderivative to get to the original problems. Okay. Any questions? All right. Let's. Oh, I didn't get my notes ready. Where are my notes? So we're going to come back and take a look at vector valued functions as an abstract object, and then try to look at specific derivative rules. Remember, we're kind of skipping over the limit ideas. We're kind of going straight into the derivatives and integrals of things. So just like when we talked about the dot product and the cross product, there was a bunch of properties. So there's a bunch of properties for this as well. We have a set of rules here that kind of mimic a lot of the rules that we already know of with regular functions. Like the sum, the derivative of a sum is the sum of the derivatives. And the derivative of the difference is the difference of the derivatives. That's that first one. If we have a constant times a function, the derivative of that is just taking the derivative of the function and multiply it by the constant. The next three, number 3, 4, and 5, is I don't want to say identical, but it kind of mimics the product rule. But you have to know what the multiplication that's happening here is. Like the first one, it's f of t, and f is a scalar function, just a regular function, and u of t is a vector function. So f of t is a scalar, u of t is a vector, and so this multiplication is actually a scalar multiplication when you scale a vector. The next one is your dot product, and the third one is your cross product. But all these kind of mimic the idea of the product rule. All right, derivative of the first times the second plus the first times derivative of the second. So same thing with the dot and the cross products. And then the last one is more like a chain rule. So let's take a look at an example of number 3, because I think that one specifically is interesting, and this is a good time for us to try to figure out, the difference between a scalar function and a vector function. So let's let f of t be a scalar function, and so let's make up a scalar function. I think t squared was a good function, and u of t is a vector function. So we could do this in 2D or 3D, but in any case, we're going to have components. And so let's make up, I don't know, should we do a sine t, comma, and e to the t or something? And let's keep it in 2 dimensions, but you can easily take this to 3 dimensions if you want. So if you want to take the derivative of this, according to this formula, it's like taking the derivative of the first times the second plus the first times the derivative of the second. So these derivatives, let's see if we can work this out. So f prime of t is 2t, and u prime of t is equal to, is it positive? It's positive, right? Cosine t e to the t. So according to this formula, we have the derivative d dt of t squared times sine t e to the t is equal to derivative of the first, so the derivative of t squared, which is 2t, times the second, sine t e to the t, plus the first, which that's just f of t, that's t squared, times the derivative of the second, cosine t e to the t. Okay. Now we can sort it out, simplify it out if we want. Or we could leave it like this. I suppose it's fine. But that's how we take the derivative of scalar multiplication.
So this would be the product rule of scalar function?
It's product rule of scalar times a vector. So scalar multiplication. The second one is a product rule for the dot product. And then the last one is a product rule for the cross product. But if you remember in your head, it's the derivative first times the second plus the first times the derivative of the second, then that's really all you have to remember. And that's the product rule that you already know in your head, except you're extending it to these slightly more complicated products. So when we say scalar function, it's important that you know the scalar function is just a regular function that we've dealt with already back in pre-calculus. And just to differentiate that from a vector function is something we're learning now, which is essentially a bunch of functions put in the slots for a vector. And that's all there is to remember about that. So when you see a function denoted without being bold-faced, then that's your regular scalar function from pre-calculus. If you see a function that's denoted with bold-faced, then that's what you would look at as a scalar. All right? So that's just this example. You can look at the book for the examples of the other ones, or maybe when you guys are working on homework, you'll run into more of these examples. We'll definitely be playing with these properties as we go along and further in our lectures. And we'll invoke some of these along the way. All right, let's move on to, what's this definition here? Integrals already. So integrals is because these vector functions have functions in each of the components. The derivative is just component-wise differentiation. The integral is the same thing. It's component-wise integration. We're going to most likely be dealing with more indefinite integrals than we are with definite integrals when it comes to these things. But it's still going to be component-wise. The only tricky part to think about is that for each integral that you take in each of the components, you may need to include an arbitrary constant. And there's two choices to do that, to deal with that. One is to literally just put each of these constants for each of these slots as you integrate it. The other way to do that is to write and collect your arbitrary constants as one vector. So this C with an arrow on top would just be your arbitrary constant for each of the components. Okay. I'm going to steal a problem, one of the problems that we were just working on, 2, 0, e to the t. Let's say we had a vector valued function that was 2, 0, e to the t, and we want to anti-differentiate this. So essentially what we'll be doing is we're going to go into each of the components and then take the derivative, or the antiderivative. So we take the antiderivative of 2, that's 2t, and then we would have a plus c. Now, we can establish this now or later if we want a norm for our class. Do we want to add a plus c for each component, or do we want a plus c vector at the end? Plus c vector, I don't know which is easier. It's all the same, to me at least. Plus c at the vector? All right, so remember that there's something in here that we will eventually add on. So that's the antiderivative of 0. That's just constant, right? So the constant's already sitting here. See, already maybe the other way might have been better. Let's do it the other way. So let's put a plus c in each of the components here. Only because antiderivative of 0 is a constant and that plus c is sitting in that vector outside. So let's keep it here for now. And then e to the t, the antiderivative of that is e to the t again, plus another constant. C3. Yep. Thanks. Okay. So that's pretty straightforward, right? Taking derivatives, pretty straightforward. So now let's well, it depends on the problem, right? It depends on the problem. If what you're doing is you might need to solve for these C1, C2, C3. Well, let me tell you now. Since we're dealing with, since I did call it the A vector for acceleration, and I stole it from the acceleration from the previous problem that we had, we can build up on this. So the antiderivative of acceleration should give us some sort of velocity, right? So this is the velocity vector. And I know that the velocity vector, v of 0, what was v of 0? That's r prime of 0. It's 0, negative 1, 1, right? So let's put 0, negative 1, 1. So if we know a piece of information about the new vector function that we're trying to obtain from taking the antiderivative, if we know an initial value, they would call it, then we should be able to solve for those arbitrary constants. So let's see if we can solve for those arbitrary constants. This says when t is equal to 0, v of 0 should be equal to 2 times 0 plus c1. There's no t's for this one, so I'm just going to put c2. And then there's a e to the t here, e to the 0 plus c3. And this is supposed to equal to this value. Let's work this out. 2 times 0 is 0, so this is c1. This is c2. This e to the 0 is 1. And this, according to our initial condition, is supposed to be 0, -1, 1. So we should be able to solve for C1. Should be able to solve for C2. And with a little bit of work, we should be able to find out what C3 is equal to. So 1 plus C3 is equal to 1. Subtract 1 from both sides. C3 is equal to 0. Right? Yes?
Can you take integrals with vectors as limits?
Limits.
Yes. Therefore, integrals with vectors as limits.
The answer is probably yes. I need to know exactly what you're talking about, though. We'll talk after class. But probably. Does somebody else have a question back there? No? We good? All right, so now that we know that, we can actually confirm that based on what we found to be our C1, C2, C3, that our velocity function is going to be 2t plus 0, comma, -1, comma, e to the t plus 0, and that's your velocity function. Does that make sense? A 2t from here, and that's the antiderivative of 2. There was a C1 over there, but we found C1 to be equal to 0, so that didn't factor in. I plugged a C1, C2, C3 into this antiderivative step. Okay? We could do this again to see if we can capture our position. Let's do it again. So the antiderivative of the velocity should be the position, and given our initial position, we can figure that out. We can get our exact formula for our position function. So R of t should equal to the antiderivative integral of v of t. So this is in the blue right here. Take it term by term. So the antiderivative is t squared plus c. I already used c. Let's use d1. -1 times t plus d2, your arbitrary constant. And then here we have e to the t. So e to the t, antiderivative e to the t is e to the t. And then we have our third arbitrary constant. Now for us to solve for the arbitrary constants, again, we need an initial condition. And the initial condition, if you guys remember what it was? 0, 3, 1. So if we know an initial condition, we should be able to solve for our arbitrary constants. So let's do that. We have R of 0 is equal to 0 squared plus d1. This is negative t. Oops, that's 0. So let's put 0 there. Negative 0 plus d2. And 1 plus d3. E to the 0 is 1. So when we solve for this, when we set this equal, because it's supposed to be equal, when we set these two equal to each other, we're going to get d1, comma d2, comma 1 plus d3 equal to 0, comma 3, comma 1. So again, we get d1 is equal to 0. d2 is equal to 3 in this case. And then d3 is equal to 0 again. And so we have our position function, which is t squared plus d1, that's 0. We have negative 1, negative t plus 3. And we have e to the t plus 0. And so if we did it right, it should be the same as the example that we started with. So this is just plugging formulas in. Michael? Oh, because that was kind of given to us as our initial position. We stole this from the problem. R of 0. We got R of 0. It was given, yeah. If you didn't have that, I would just make up a different one. Whoever's giving you the problem would make that up. Let's say, oh, this is 15, in which case you would use 15. But this piece of information should be, well, it depends on what the problem you're working on. If we're working on a projectile problem, then this should be given. Oh, if it's not given, then you might have to find it using logic and using whatever scenario you're dealing with. Okay. So let's identify these and actually call them initial conditions. So this is the initial position. This over here was the initial velocity. What? Yeah, the initial velocity was also given. And it's usually at 0, unless for some reason you want this to start with a different time. Yeah. So d3, this is tricky because when you put 0 into this function, the antiderivative that we got, when you put 0 into e to the t, it was equal to 1. So this says 1 plus d3 should equal to this. So 1 plus d3 is equal to 1. And so when you solve for that, d3 actually is equal to 0. And so you have to be careful with the initial position and velocity. Now, a lot of times, the constants, c1, c2, c3, d1, d2, d3, would just equal to whatever these initial conditions are, a lot of times. But there are some occasions where if your function involves an exponential, for example, or a cosine function, where if you put 0 in there, you don't get 0, like e to the 0 is 1, cosine of 0 is 1. When that happens, then your initial condition is not going to be what your constant's equal to. Like this one, this is 2t. So when you put 0 in there, that's just equal to c1. So your c1 is going to be equal to whatever the original value was when the initial condition. But for these cases where it's not the same, it's going to give you a different value. So I think if you're dealing with polynomials, your initial conditions will end up being your arbitrary constants. Okay. I know for most of the examples in physics, when you guys deal with projectile problems, you're just dealing with polynomials. But if your acceleration happens to be non-polynomial, like it's some rocket, strapped in the back or something, and then spins around, so it gives you an extra acceleration that goes in different places, then it's not a constant anymore. Okay, so that's the antiderivative. Now let's talk about some more interesting stuff. I don't want to go there yet. A blank page. I'll start off with a blank page. Should we stick with that function, or do we want to come up with another function? Another one? All right. So let's come up with another function. Do we want like one of those helix or those things, roller coaster things, or you want to shout out some functions? We're going to take derivatives of these things, so just be careful. It's not being careful. 4t. Really? They're not being careful. There. One more. All right, remember the derivative. We need to take derivatives of these things. So tangent, there's some undefined parts in tangent, right? Like pi over 2, something like that. So we need to just be careful about that. All right, let's take the derivative of this. So derivative sign is positive, right? Positive cosine, but there's a negative in front, so it's negative cosine 4t, and then you have to do the chain rule, so there's an extra 4 that comes out. We have a 6t, and then 2/3. Anybody remember derivative of tangent? Secant squared t. All right. Good. Now let's find a nice starting point. 0 is always a nice starting point. Oh, I forgot to put prime. This is prime, right? Yeah. Oh, yeah. Maybe we will take the acceleration too. R double prime of t. Okay, this one still isn't too bad. Derivative of cosine is negative sign. That's going to make this a positive. And then there's going to be an extra 4 that comes out. 16 sine 4t, 12t. And then secant, derivative of secant is secant tangent, right? So this is going to be 2/3. And then now let's take the derivative of this. 2 secant t times a derivative of secant, which is secant t to the first, secant t tangent t. We have to use the chain rule, right? Drop the 2 down, inside, first power, and then the derivative of the inside. It's a good thing we're reminding ourselves how to take derivatives of things. Did I do this correctly? You don't know. I don't know. You don't do the chain rule? this is a secant t squared, right? Secant squared t?
It's just 2 secant t.
Are you sure? What?
We have internet. Use the internet.
Times secant tangent.
Yeah.
Well, no, there's a t here, so it's understood that this is next to it.
It's 4/3 tangent secant squared.
No, that's what we got.
I got 2 secant squared t tangent.
Yep. That would be it if you simplify it. Okay.
So let's do inverse cosine.
If you want. No. We're going to do something. We're not going to integrate. Really? So anyways, whatever this thing looks like, we'll actually mimic this with a better graph. So these two vectors, the acceleration vector and the velocity vector, might look something like this. But sometimes we're curious when we're running along a particular curve like this, we might be interested in not necessarily the speed, but we might be interested in just making this into a unit vector. Do you remember how to make a vector into a unit vector? Divided by the magnitude, right? So let's take our R prime and find its magnitude. So the magnitude is going to be 16 cosine squared 4t plus 36t to the fourth plus 4/9 secant to the fourth t. But I'm taking the derivative. Yeah. I think I did that right. So I essentially took each of these and I squared them and I added them and put under a square root. So if I divide R prime with R prime magnitude, I'm going to get a unit vector. So on the side here, I'm going to call this the unit tangent vector. And the unit tangent vector I'll denote with capital T, and it's a vector, so I'll use an arrow on top. And this is equal to the velocity vector, the tangent vector essentially, so that's R prime of t divided by its magnitude. Okay. So let's actually find this for t is equal to 0 in our example. Find t of t, let's call it t of 0. Find capital T of 0, which is a unit tangent vector at time t is equal to 0. No, you're shaking your head. I just put 0 in, right? So let's put 0 in to the top. I get 0 and 0 and 0. That's no good. Oh, wait, I put it into the wrong one. It should be -4, right? Let's try that again. Not getting away that easy. So we put 0 into the velocity function, right? So that's cosine of 0 is 1, -4, times 1 is -4. And then now we have a 0 here. So anybody know what secant of 0 is? It's the cosine, right? 1 over cosine. So it's 1, 2/3. Now comes the fun part. Let's put 0 into the magnitude. So 16 plus 0, 4/9. Square root of So we can make this into one vector. So let's multiply it by the reciprocal. Negative, the 2 and the 4 cancel. -6 over √5. 0 and the 3 and the 2 cancel, 1 over √5. And if you take the magnitude of that, we should get 1, because it's supposed to be a unit vector. All right. What we're doing here is we're creating a frame. And we got one. When we think about a frame, it's like three vectors, like the ijk vectors. But the ijk vectors are special vectors for the x direction, the y direction, and the z direction. What's happening is that if you're traveling along on a curve, you can set your own axes for where you are. So imagine yourself in a roller coaster, right? Imagine yourself in a roller coaster, and you are sitting in the roller coaster. Going straight ahead is going to be the tangent vector, and we can think about two other vectors going straight up and going to the left or to the right side of your body. Okay? And if we make all those nice unit vectors, we have a frame for you as you go around the roller coaster. So wherever you are in the roller coaster, you can see everything else, and you can have the perspective, from your three-dimensional frame where everything else is existing. You see a bird on the side, on the right side, you know that it's only going to be on your right side relative to you where you are at some point in time. So the unit tangent is the first of those three vectors that we're looking at. We're going to find the other two vectors next time, and then we will take a look at how the Frenet frame works. This is called a Frenet frame. I'll show you more pictures next time. All right, see you guys. What?